Ever since the Big Bang, there have been celestial bodies that have ravaged their way through the known universe. They've devoured stars, planets, they've even devoured each other. These celestial objects are black holes.
Black holes are formed when supermassive stars collapse. These stars collapse when nuclear fusion inside the core of the star collide hydrogen atoms into helium, which releases an incredible amount of energy. This energy, which is radiation, pushes against gravity. Nuclear fusion continues until iron is able to be produced inside the core of the star, which doesn't generate any extra energy. Mass builds in the core, and gravity increases while radiation decreases. This destabilizes the star and causes it to collapse. If the star is 2.8 times the mass of our sun or larger, then it will become a black hole. Even before the recent upload of the black hole in the Messier 87 galaxy, we've known about them for a while and have had some interesting theories. Black holes receive the name for their unnatural darkness. The reason why we cannot see a black hole is because the photons, or particles of light, can escape the extreme gravitational pull, and they are the fastest moving thing in the universe because theoretically they have no mass. In order to actually escape a black hole, you must travel faster than the speed of light, which is currently impossible. This is the escape velocity equation. In 1905, Albert Einstein theorized the theory of relativity. From this theory came breakthroughs in gravitational lensing, gravitational waves, and gravitational redshift. The main one I'd like to talk about now is gravitational redshift. The principles that follow this are similar to that of the Doppler effect, which was developed by Christian Doppler in 1842. If a car drives down a road with its horn on, the person in front of the car will hear a higher pitch than that of the person behind the car. This is because the wavelengths of the horn in the front of the car will be more compressed due to the motion of the car, which will then increase the frequency of the horn due to lambda's relationship with frequency, which is represented by the light equation. This same concept can be applied to light waves. If observer A is falling into a black hole and is being watched by observer B, who is at a safe distance, which is approximately the radius of the black hole away from the event horizon, which is visible due only to relativistic jets, observer B will see observer A turn infinitely red until our eyes can't perceive any more changes, until black is all we see. This is because the photons that are reflected off of observer A gradually absorb into the black hole, and the photons seem red because the light waves slow down due to the black hole's gravitational pull. To observer A, observer B will actually blue shift. To observer A, it will perceive time as moving faster than observer B, who will see the father's time as moving slower. This is another result of extreme gravitational pull. Another important concept that came out of Einstein's theory of relativity is that space and time are an interconnected fabric. They flow like a wave, and when a larger mass, for instance our sun, is present, a dip is formed in that space-time fabric which attracts or pulls in surrounding masses that are less than that of our sun, like our planet. Black holes, however, rip that space-time fabric to the point where there is no perceivable ending.
Black holes are all around our universe. There's even one in the center of our galaxy in the constellation of Sagittarius. Black holes are one of the many things that we have yet to learn more about and truly understand. My name is Ian Harris, and thank you for your time.